Alright, so this is time for our overdue video on the parallel axis theorem. So the parallel axis theorem is really useful because in your book you saw some expressions for the moments of inertia of an object when the axis goes right through their center of mass. But it's not always true that that's where the axis of rotation passes through. So the parallel axis theorem allows us to find the moment of inertia through an axis that is parallel to the one that went through the center of mass, but it's just displaced. So in this picture, keep in mind they're trying to be really general. We have this blob, doesn't really have any special shape, but the way that it's set up is the origin of the coordinate system is determined to be the center of mass of this object. And so when you're calculating its moment of inertia, so we're going to find the moment of inertia through when the axis passes through this point, using the idea that it's the sum of the mr squares. Now here's a particular mass right here, and its x-coordinate is x sub I, its y-coordinate is y sub I, so r sub I squared is equal to x sub I squared plus y sub I squared. It's just the Pythagorean theorem, so we could write this as the sum of m sub I x sub I squared plus y sub I squared. Okay, so that's how we would find the moment of inertia when the axis is through the center of mass, which is our origin of our coordinate system. So now what we want to do is we're going to move the axis to point P. And right here is point P, right here, the blue one. So the coordinates of point P, the x-coordinate is A, the y-coordinate is B. So that's where it is. So now that's the axis that we're measuring the moment of inertia about. So we're doing, again, the sum of the mr squares. I'm going to make that a prime just to differentiate it because it is a different distance. So now we're measuring the distance from this point, and this is where the mass is. So the x distance is x sub I minus a, and the y distance right here is y sub I minus b. So this looks like this. So that's how we calculate the moment of inertia when point P is our axis. So we're going to expand that. And so we expanded both of those and got two different quadratics. Now if I look, I can notice that I got x sub I and y sub I squared, and so one of those terms is m sub I x sub I squared plus y sub I squared, which you should recognize as the center of mass moment of inertia. Then we have some other terms. We have 2a times the sum of m sub I x sub I plus a squared times the sum of m sub I. And we also have, oops, sorry, this should be a minus sign. And then we minus sign here, 2b m sub I y sub I plus b squared m sub I. So these, we've just kind of separated out the terms that we see above, and then we have all this. So I'm going to write this on the next page just to remind us. this last term. So, and remember that we said that this right here is the moment of inertia when the axis goes through the center of mass. Now we have a couple terms that look kind of messy, but let's look at our picture. And so we have this term and this term just look like a mess, but we're going to be able to get rid of those pretty easily. If you remember, the x center of mass is defined as m sub I x sub I over m sub I. And the y center of mass is defined as m sub I y sub I over m sub I. But keep in mind, for this particular picture, we put the center of mass at the origin, so both of these are 0. So that means that this denominator in both of these expressions has to be 0, and that's what we see with these two terms. So basically, this is 0 and this is 0. So now we can simplify this a lot. We have the first expression, which we've already identified as the moment of inertia of the center of mass. Then the terms that are left is a squared plus b squared times this total mass. A squared plus b squared is equal to hypotenuse squared, which is d. That's the distance we've moved the axis. And the sum of the mass is just m. So the parallel axis theorem, now we've got it, is the moment of inertia when the axis goes through the center of mass, and then what you do is you add a term which is equal to the mass, and then you take the distance that you've moved the axis and you square it. This is the parallel axis theorem. Let's try it out. Oops, we don't need all these slides. Okay, so you might remember in your book there was a picture of a rod where the axis, so the rod has a length of L, and it's spinning around this axis. This axis goes through the center of mass. And this moment of inertia is 1/12 ml squared. Then we also saw a picture of a rod that looks identical to that, has a length of L, but the difference is this is rotating about its end. This moment of inertia was given as 1/3 ml squared. We can actually get this expression using the parallel axis theorem. So if we want to find the moment of inertia when it's rotating about its end, we're going to take the moment of inertia about its center of mass plus m d squared. Now in this picture, in this situation, what's the d? D is equal to L over 2, because from here to here is L over 2, and that's the distance that we've moved the axis. We've moved it from here to right here, and that distance is L over 2. So the moment of inertia when the axis is about the end is 1/12 ml squared plus m times L over 2 squared. So that's 1/12 ml squared, and then this is 1/4 ml squared. Now we can find a common denominator. 12, 1 plus 3 ml squared is 4 over 12 ml squared is equal to 1/3 ml squared. And we got it. That's just one example of using the parallel axis theorem. So hopefully this makes some sense and helps you understand it a little bit better.